Okay, let's get started. Hi, everyone. My name is Ewen Cheslack-Postava. I'm an engineer at Confluent, and we're working on what we call a stream data platform, which helps you store, process, and ultimately derive value from large quantities of real-time data. Stream processing is a paradigm that allows you to efficiently process that real-time data, and today I want to explain some key challenges and abstractions in stream processing, and also introduce a new stream processing library that we're working on. So to explain what we mean when we say stream processing, I want to look at three different paradigms for writing software. There are a lot of frameworks that you can use in order to define different programming paradigms. Today, what I want to look at specifically is how programs get their input and produce their output. So you're probably already quite familiar with the first two, and of course the third is stream processing. I'll talk briefly about each and explain how stream processing is unique. So the first is the request-response type system. And request-response systems are synchronous and tightly coupled. So the idea here is you have one input, which might be an actual request for data, or it might actually be submitting data. And a single response comes back, and you block on that response coming back. I've simplified things here. Obviously, that computer may also be backed by an entire data center full of other services, so there's a bunch of other interactions going on there, but the important piece is that you get one input, one output. The way you scale these types of systems, since they're synchronous, is that you have multiple instances of each service. And the key characteristics are that latency is really important, and things get tightly coupled. So you making this request are very tightly coupled to this computer serving the response. Any failure or degradation in any of these services can affect many downstream services that are consumers. So sort of very obvious example of this would be something like an HTTP request. Or really, actually, most common network protocols fit into this category. Anything sort of client-server oriented. You send a request for one resource in an HTTP request, you get one resource back. So in contrast, there are batch systems. The major difference here is that the expectation around latency is much lower, and there's looser coupling. So in this case, you sort of have a bounded set of data, which you insert into the system at some point, and then ask it to run some sort of job or query or something on that data. And then eventually you get sort of all of that data back out. It's, as I said, not as sensitive to latency. Obviously, you're working on oftentimes hours, sometimes days later, getting the response. However, this bounded view of data, where you get this entire set all at once, allows these systems to be implemented very efficiently. You can optimize for things like data locality. You can reorganize the data to match processing needs. So another very popular example of something like this would be something like MapReduce, where you collect all of your data into HDFS. You define the exact set of data that you're going to operate over, submit the MapReduce job. It goes off and figures out where to sort all of that data, put computation on the same nodes as the data, run it very efficiently, and then at some point later it comes back. Maybe you do this every 24 hours to update some data set that you're tracking. Smart systems figure out how to co-locate data in computation. This makes things very efficient. But eventually, all of the data comes back out as sort of another set of files in HDFS. It's this bounded, fixed set of data. So stream processing sits somewhere in between those two. The request-response model used one input, one output. Batch used whole set of input, whole set of output. For stream processing, we have sort of some inputs, and some is a little bit vague here because it can vary, but you send some inputs into the system, and then at some point it decides to output some data. You send some more inputs, it sends some more outputs. An example, just to make this a little bit more concrete, I'm going to go through a couple of these. This is sort of a classic example, a windowed aggregation where you take a window of inputs. The window could be time-based, as I've drawn it here. It could be based on the number of events, a variety of options there. And you then aggregate that data, and each of the outputs is a count. So very simple example, but the inputs and outputs are coupled in the sense that each output is tied to a window and some set of inputs, but they are not a one-to-one mapping. So stream processing, as you can see here, is actually a generalization of those two extremes of batch processing and request response. The fundamental shift here is that stream processing is actually viewing data as unbounded. It's an unbounded stream. In request response, you have a single item and a single response. In batch processing, you fixed your data set up front. In stream processing, we just sort of accept the fact that you're never really going to stop adding data to your data set. So what's the benefit of this style of processing? A lot of times stream processing is confused as just meaning low latency processing, but it's actually a lot more than that. Stream processing, the way I'm going to define it today, is hugely beneficial because it gives you control over a number of trade-offs. Specifically, I mentioned latency and efficiency. And if designed properly, it allows you to also get correct results like batch systems do. I'm going to go through a couple examples and then revisit those trade-offs. So some systems that you are probably very familiar with are actually sort of stream processing systems under the hood, but you might not really think about them that way. So in particular, databases, relational databases. The way that these databases operate is that they handle this incoming stream of transactions, or simplified to just single writes if that's easier. They accept each of these transactions. They update some internal state, so that's sort of their current view of the data set. Along the way, they're able to handle additional queries on the current state of the system. In some sense, if you think of all of the transactions sort of until the end of time as being the ultimate final state, and if you ran a query then, that would be the correct output, these intermediate queries aren't technically correct in that sense, but they're correct at the given time. The database never expects this input to end. It expects the stream of transactions to continue to keep on coming in, but it can generate these intermediate results. Something that's probably a little bit closer to home and something that you've probably implemented a number of times yourselves are sort of stream processing microservices. And so this actually looks a lot like the database, except you're implementing some of the pieces yourself. So if we sort of take that aggregation example, we can imagine accepting some input stream of events. And this input stream of events might be something like external user requests. And then generating some intermediate aggregate result from that. So for example, we might keep track of those windowed statistics, or we might just keep track of a total count of views over all of time. We can then write an application which handles queries from some other service or from users to get this data back out. So this is something you've probably actually built yourself and may not have even realized that you were doing stream processing application. So if you have actually encountered the sort of modern stream processing frameworks directly, you may have heard some vicious rumors about them. It turns out all of these are really misconceptions about stream processing in general. So stream processing doesn't imply transient data. It doesn't imply approximate results. It doesn't imply lossiness. It isn't a requirement that you have a batch system in order to get correct results out of the system eventually. Many systems do have these limitations. They decide to make certain trade-offs that cost them things like correctness, but they're not fundamental limitations of stream processing itself. So in particular, the reason there is this misunderstanding about stream processing frameworks is because they have to manage sort of a tricky set of trade-offs. While processing unbounded data sets, the trade-offs involved are, as shown here, correctness, cost, and latency. Oftentimes, stream processing systems are designed to optimize for some of those trade-offs, in particular latency most of the time, instead of being designed to offer sort of a control between which of those you want. Because some applications might care about correctness, but others might not. Some might need low latency. Others are okay with it, waiting a few seconds. Some might also not be okay with the cost required to optimize along those other two dimensions, and so they might, in order to save cost, trade off that latency or correctness. But the claim I'm making here is that you actually can make stream processing systems satisfy sort of different sets of constraints, including things like correctness, and do it efficiently like batch systems do. In fact, batch systems and stream processing systems are actually quite like each other, except they take a different set of trade-offs. Stream processing systems tend to favor lower latency. Batch systems tend to favor correctness. It actually turns out, and we'll come back to this later, that you don't have to have one or the other. When what you actually want is sort of a unified approach where you can sort of trade off between these things. So sort of the summary of stream processing itself is that actually stream processing isn't really any more complicated than it's a function of what happened, and what happened is some set of events, and what happened is what happened up until now. And so we can process the data up until now, and we'll continue doing that continuously. What I want to talk about now is sort of the two different approaches you can currently take to build stream processing applications. So the first is the do-it-yourself approach. This sounds a little bit silly. Of course, you can do it yourself. But actually, I explained one example with the microservices, which admittedly was hand-wavy and simple. But you can actually just consume data yourself, process it as a stream, and then either write outputs or serve outputs. And so that sort of looks like this, where if you frame it in terms of the actual message streams, you have some process which consumes data off of some message queue. I'm going to talk a lot today about Kafka, but none of this is actually specific to Kafka. You can do this with other message queues as well. Kafka just does it fault-tolerant, scalable fashion. But you just read this input stream of events and compute some statistic over some window, and then produce the output to wherever you want to store it. So this looks really simple. And it is, and that's actually a huge benefit of this. You can adopt stream processing today without really much effort. The drawback here is that there are a couple of things that we're missing. We have a single process. We don't have it running on multiple machines. It won't scale. If anything fails, the data actually is transient. We're probably getting approximate and lossy results. And so this may not be the best solution, but if you can deal with some of those limitations, maybe this is a good way to go. Since you are working directly with the sort of message queue yourself, you're managing the process yourself and all of the details, you're going to face a lot of challenges. And in particular, this is the one slide that if you take nothing else away from this presentation today, you should know and understand this slide. These are all the hard problems that stream processing frameworks are going to solve for you. So I'm going to walk through these one by one and just sort of give a quick explanation of what I'm talking about on each bullet point. So partitions and scalability, that's the sort of single process problem that I just mentioned. If you only have a single process and it dies, you probably lost state. You can't actually scale out. You don't have a way to split up the data and process it in parallel. Figuring out how to do this is actually pretty tough. You need to do this in a way that you get data sharded across multiple processes in a way that you can actually correctly compute things. I'm going to come back to how Kafka helps us solve that in a bit. Semantics and fault tolerance. So I mentioned that if a process fails, you're probably going to lose some data. You probably don't even have a hot standby in order to continue serving data. But there are actually some really tricky problems around how many times you process data as well. So if your process stays up, it's really easy to guarantee that you process each event once and that you don't get incorrect results because you, say, double counted somebody viewing a page. If you have to deal with faults, that becomes a lot harder. There's no system is going to guarantee you exactly once processing without some help from you, and it gets more complicated because oftentimes stream processing applications have to involve external services where there are side effects. But your stream processing framework can provide a lot of support to make this feasible, or at least to understand the implications if you're not getting exactly once processing or even exactly once delivery of messages from your message queue. So a third issue is state. Basically, every stream processing application that's interesting needs to track some sort of state internally in order to keep track of, after each message, what information it's gathered so far. In the aggregation example, this would literally just be a single count where we're just counting how many page views there are. Any operation that spans multiple records, like an aggregate, will need this state, and you need to figure out how to store that locally. And you also need to figure out how to make it fault tolerant. So when that process dies, where did that state go? How do I recover it and get back to the place where I was when I start consuming messages again? Okay, and so fourth item is windowing in time. So if data is unbounded, you at some point have to choose some window over which to compute anything, any statistic. And you can't wait for the data to finish or to reach the end or anything like that. There are a lot of details around windowing that are crucial to making stream processing work correctly. you need a variety of windowing support. Implementing that yourself at a bare minimum would be annoying, and it is useful to have those tools in place already. But in particular, windowing deals obviously a lot with time. And time is probably one of the trickiest problems in computer science. Anybody who's dealt with dates or timestamps, time zones will know that. But more particularly in the case of stream processing, it's a difficult problem because we care a lot about distributing work. And in distributed systems where we have multiple machines, each of which have their own concept of time, we have to rectify those different views and make sure everything is actually consistent. In addition, I'm going to come back later to the fact that we actually have multiple concepts of time in stream processing systems. This is a relatively recent development, but it turns out to be crucial for getting correctness in stream processing. And then the final issue is reprocessing. You're going to probably have bugs in your code or missing requirements or have to make modifications to the system after you've started deploying it. But if you've already consumed a bunch of data and discarded it, suddenly we have this problem of how do I actually bootstrap the process again? So page view counts is a good example of this, where if you literally want the total number of page view counts ever recorded, if you've discarded a bunch of data, you can't just go back and recompute that. The stream processing framework oftentimes won't provide direct support for reprocessing, and part of this is motivated by the fact that you need a storage system for that data in order to be able to go back and reprocess it. But you want it to have at least enough support in the system that if you wanted to, and your storage layer has the support for it, you can go back and reprocess data. So that's a lot of hard problems, and hopefully this gives you an idea of why the do-it-yourself approach is probably not the greatest solution unless you can give up a lot of these things. So of course, approach 2 is use a stream processing framework. There are a ton of these out there now. I've listed sort of the most popular ones here, but honestly, as of like the past year, they're popping up left and right, so I don't think I could even fit them all on here anymore. Spark, Storm, Samza, and probably now Flink are the most popular ones. The goal for all of these systems is to enable users to express stream processing operations through convenient APIs. And usually that means that even if they have a lower level API, they also have high level convenient DSLs for expressing things like maps, transformations, aggregates, groups, stream joins, etc. And their goal is basically to abstract away all of that other stuff that I just talked about. You shouldn't really have to worry about any of that aside from understanding that those concepts exist in the framework, and the rest of it is taken care of for you. All of these systems vary in the exact feature sets they provide. They have slightly different APIs, but to a first approximation, they all provide basically the same service. So these systems are awesome, and we love them. There's a ton of innovation happening in this space. The frameworks themselves are quickly improving both in feature set and efficiency. And this is great, but there is one downside, which is that it turns out the way that most of these systems tackle stream processing results in a lot of moving parts. Once you write a stream processing application, you aren't done. Just because you've written, say, the Java code for it doesn't mean that you're ready to actually deploy. There's a whole mess of stuff around configuration, deployment, how you get jars on the machines, managing the cluster, operations. Each of these systems operate in a mode where you run a separate cluster. Maybe your ops team manages it. You submit jobs, and they run on the cluster. It's nice because that makes it trivial to sort of have them automatically parallelize and distribute. But that's a lot of overhead. What this actually results in, too, because of the sort of combination of the feature sets and the way we deploy, is sort of this example architecture, which is actually called the Lambda Architecture, which involves sort of even more moving parts. So beyond just the stream processing pieces, we actually have to involve additional pieces. So a common approach would be to write data into Kafka, or whatever message queue you prefer to use, and you then pipe it down into your stream processing framework. Your stream processing framework takes your code, figures out where to run it, executes it, and you generate some output data. And let's say that goes into some output data store, which you can then easily query. So now you've got your sort of real-time approximate results for page views. However, that data will eventually get cleaned out of Kafka, and so if we want to be able to go back and make modifications, like we have a bug in our, for some reason, a bug in our counting code, or we want to filter a certain class of users, maybe we have crawlers that are messing with our statistics. In order to get correct results over the long term, we actually have to also pipe our data into Hadoop that for long-term storage, and then also run code on something like Spark or MapReduce in order to backfill all of those results from when we update our data. And then that ends up in some other data store. The output there, since the batch system, is probably HDFS, and maybe you then pipe that into some easier to query interface. And what this results in is then an even more complex downstream application, which has to figure out when it should be going and querying the real-time stuff, when it should be going and querying the backfill data from the batch system. So now we have even more moving parts. We also have a Hadoop cluster. Like in this model, we can't really adopt stream processing on its own. We have to also adopt some batch system in order to provide that backfill reprocessing. So this got really complicated. The number of distributed systems that you have to maintain and manage and monitor has become pretty big. Honestly, it's not even, the diagram isn't particularly complex, but it's not particularly easy to understand in the entire system. You've probably written your code twice. If you're lucky, maybe you can reuse a lot of it. So if you use Spark streaming in Spark, maybe a lot of the code can be reused. Oftentimes, that's not actually the case. So the reason we started looking at these systems and trying to tackle the problem in a different way is because for distributed systems, coding is usually the easy part. Debugging is harder, and then operations, which is an ongoing problem, is oftentimes the hardest thing. And so what we want to do is figure out a way to reduce the operations overhead and figure out if we can reduce the number of moving parts here. And so in the case of adopting Kafka, Kafka actually does already provide a lot of these important primitives. It's able to provide them in a way that you get some of those important features that I mentioned on the sort of challenges slide, basically for free, as long as you commit to using Kafka as your storage layer. So what I want to do is run through sort of Kafka at a sort of 10,000-foot view, not a deep dive. I'm not going to go into any real implementation details, but enough to give you a sense for how its functionality maps into stream processing and how it can simplify stream processing frameworks. So at a high level, Kafka is just another pub sub message queue. It has producers. There's a cluster of brokers which actually store data. Brokers then accept the data, write to their log, and then consumers can grab that data. From this picture, it looks a lot like other message queues, but it actually has a couple of important differences that allow it to scale. So in particular, its implementation is based around the idea of a log, and hopefully you should see why this fits very well with stream processing, given the similarity of the pictures so far. By writing to a log, what we mean is that you always append data to the end of the log, and then when we consume data, we always read sequentially from the log. There's no random access throughout the log. This results in very high performance. It allows you to get very high write throughput and read throughput. And it turns out that this restriction on accessing data is rarely an issue. Most applications access the data this way anyway. I said it's pub sub, so what that means is that we can have multiple subscribers. So downstream systems can consume the data multiple times. Each downstream consumer will consume each message only once, but each message can be consumed by multiple downstream readers. They each maintain their own offset in the log, so they don't have to be synchronized in any way. What this means, however, is that there's no acking like you would often see in other messaging systems. So instead of acking, the data still has to be cleaned up somehow. You can't just clean it up on ack. We don't have to track any acking, which actually makes this a lot more efficient, but we need to figure out when we can delete old segments from this log. In Kafka, this works on a time-based or data size-based policy. So you might keep 7 days worth of data or up until 100 gigabytes or something like that. This approach is simple. It avoids having to account for those individual messages and actually works for a vast majority of use cases. Okay, so that's sort of one log, but actually when you write to Kafka, you write to something called a topic. A topic is just a logical partitioning of messages. So for example, you might write log messages from a specific application into a single topic. These topics are also partitioned. And so actually each topic that you write to doesn't have a single sequence of events. It has n of them, where n is the number of partitions, in this case 3. And that sort of raises the question, when you produce data, how does it figure out what partition to put it in? If you don't care, it'll actually just round robin and you can put it in any partition. But usually you'll have some sort of information about how you want to group things within that topic. So for example, when I'm writing those log messages, maybe I want to make sure that all of the messages from a single host go onto a single partition. In that case, I could manually map that partition, but I can also just provide a key and it'll basically do a hash to figure out which partition to put it in. This is important because then when a consumer reads that data, when it's reading in order through each of those partitions, it'll see all of those events in order as well, and they'll all be in the same partition. And it's also important because Kafka provides support for scalable consumption. So I talked about the sort of log abstraction, sharding, partitions, and data scalability. But we also want to be able to scale out computation. So we care about scaling the storage in the Kafka layer, but when you consume data, generally you're going to go do something with it. And if whatever you do with it takes some time, whether it's applying some computation or interacting with some external system, you might need multiple consumers in order to be able to scale that processing up. Consumer groups provide this functionality. They're sort of auto-balancing partitions amongst themselves. And as I said we can have multiple consumers, which means multiple consumer groups. So as you can see in this picture, in the blue consumer group A, we're trying to sort of balance the partitions evenly. We only have 3, so there's a limit to how balanced we can get, but balance them between that first consumer instance at the top and the second consumer instance below it. It's worth noting that those consumers don't have to be in the same process. They can be on different machines. So this allows you to also distribute across multiple across multiple host systems for getting more access to more resources. This consumption is also, or the scalable consumption is also sort of dynamic and fault tolerant. So besides making it easy to scale your application from the start, it'll also handle if your application scales up or down, whether by accident, like a fault, or intentionally due to elasticity. Maybe your load went down or up and you need to increase or reduce the number of instances. So the consumer group here will, when one of them fails, it'll automatically detect that. And in this case, there's only one consumer left, so it'll rebalance all of the partitions onto that single consumer instance. Note that if you're used to something else managing your processes, like in MapReduce, consumers are not managed processes. You manage them however you want to. You can put them under something like, Mesos, Yarn, whatever. But in this case, if that instance dies and you do nothing to bring it back up, we'll continue consuming with just that one consumer instance. If you do revive it, then things will rebalance and you'll be back into a good state. So the last thing I want to visit with respect to Kafka features is around this idea of reprocessing. And I mentioned earlier that there's a limit to exactly how much a stream processing framework itself can do here, because a lot of reprocessing is dependent on the storage system. So what I'm going to explain here is what Kafka provides that makes reprocessing actually feasible if you assume that you're using Kafka. So what I want to go through here is sort of a quick example where we have a set of records, and the keys are just those letters and the values are numbers, say counts of the number of people who visited the website. Let's say that we're trying to build a dashboard off of this. And so what we do is we've had an application running where we computed these, and we've kept track of that state, and that gets stored into some table in a database somewhere. And the application actually just reads off of that database for whatever the current state is, and we get fancy dashboards and whatnot. If we go back and realize that we broke something, or like I said before, there are crawlers now and they're messing with our data, and we need to fix things up, we need to go back and reprocess the data. If we assume for the moment that Kafka can store this data indefinitely, then we can actually just do something really simple. Start up a new application, copy of the application, set up a new output database table, set the offset all the way back to the beginning of the data, and then just start consuming from there. So This, again, assumes that you have all of the data available, but of course, if you rerun the entire computation from the beginning of time, you will get correct results. In Kafka, this is nice because while I only drew one partition here, you actually have multiple partitions, so this processing happens in parallel. You can scale it up. When you need to backfill, you can very quickly get that data restored. But conceptually, what we've done is we've just gone all the way back to the beginning. We start off with an empty set of state and a new application. We still have our old application running, and maybe new data is still coming in, but reads are still being served off of that old data. We just keep on processing data, and the new database starts getting filled in with the now correct data. And eventually we reach the end, a point where we can sort of synchronize and say, okay, we're sufficiently up to date that we can swap things over, read switch over to the new state, kill your old state, kill your old application, and you've backfilled your data. Note that this involved no actual batch process. This was just the streaming process and supported by Kafka's data storage. Okay, so that's great, but of course we made this really ridiculous assumption that we actually have data for the entire span of time. That's clearly infeasible for a lot of applications. But there is something else that we can do with Kafka, which is called log compaction. And so this is useful in cases where you actually do have keyed data like that, and the computation has certain constraints, like it only actually cares about the latest value. Kafka has a feature where it will basically use indefinite retention. You can set an indefinite retention policy, but it'll keep track of those keys and then eventually deduplicate and clean them up. Within the actual stream of events, you can see the same key multiple times. So it's not like a key value store where at any given time you can read off the specific value of the key. It's still a log. It's just that at some point we went back and cleaned out some of the entries that are no longer needed because we knew the key was overwritten. With this mode, you can actually potentially store data sort of indefinitely and reprocess that entire set of data in Kafka. The old data was overwritten or deleted, and so you basically do have all of your data. If you think of this log as actually records from a database, so think of that transaction log that I mentioned before. If we actually take that entire transaction log and write those events into Kafka with the appropriate keys, you actually get an entire copy of the database as a stream in Kafka as a log of events, but we can also compact it so we can get rid of old data efficiently. So this actually demonstrates that logs sort of unify batch and stream processing. They're not actually really that different. So if you have this log abstraction, a batch process can simply wake up at some point, and it's at some offset. And then it starts processing and runs until it reaches the end of whatever the current set of data is. So it's not the end of the data, it's just the end of what we currently have. It goes back to sleep, sleeps for 24 hours, and then wakes back up and does the same thing again, and just keeps on looping. There's actually, so sort of batch systems are ones that process unbounded data sets, but they do so by sleeping, processing what's available, and then, waking up, processing what's available, and then going back to sleep. What we also have then are stream processing systems, which do sort of the opposite thing. They stay awake the entire time, and as things come in, they process immediately. And so they get very low latency, but they're constantly running and constantly using up resources. And in some cases, processing things that incrementally will be less efficient. So the reason this concept is powerful is because it gives flexibility to the program to decide whether it wants to be more batch-like or more stream processing-like. And actually, it allows you to choose something in between as well. And if you choose something that's more batch processor-like, then you get better throughput. If you choose something more stream processing-like, you get lower latency. In both cases, you can still get correctness. So given all of these primitives that Kafka provides and that stream processing frameworks can take advantage of, I want to revisit an idea that we looked at earlier, which was, what if we just had stream processing as a simple consumer, some custom code, a little bit of custom code, and then a producer to output results, and producer could be to any system, not just Kafka. The additional reprocessing and the support for sort of doing this state storage that I just discussed really only leaves a few items from that challenges section, if we assume that Kafka is being used for this producer and consumer. We already have parallelism, we already have fault tolerance, and so a lot of the hard pieces are already taken care of. We still need to deal with things like state storage and understanding how windowing and time works, and I'll come back to that. And so based on this idea that we're already getting a lot of support from the existing clients in Kafka and Kafka's implementation, we started building a library called Kafka Trains. And it's a stream processing library that allows you to express all the common stream processing operations, and it's embeddable in applications, which is a different take compared to most frameworks. It doesn't control how you configure your code, how you package it, how you deploy it. It contains two key interfaces, which actually look a lot like other interfaces that you'll see in stream processing frameworks. A low-level processor API, which is callback-based, and it provides very little support for sort of a lot of the windowing and stuff like that. And then DSL. But before I dig into the particular interfaces, I want to discuss quickly the difference between libraries and frameworks. I'm sure most of you are familiar with this already, but it's worth emphasizing. It can definitely seem a little bit pedantic, but it's actually a pretty important distinction from the perspective of somebody writing and deploying these types of applications. In a framework, the framework completely runs the show. You provide some hooks, but those hooks are very restrictive, and the framework handles all the execution. Your code executes whenever, wherever, and however the framework determines it should. A library, in contrast, is trying to provide utilities and support. It's invoked when you decide it should be. Unlike a framework, a library has no control over when how it's deployed, how it's configured. It runs on whatever configuration or cluster management system you choose to run it on. If you use Mesos, Yarn, Chef, Puppet, your own custom system, or if you're just too lazy to even monitor your processes and you're okay with them dying, that's fine too. It's worth pointing out here that neither of these approaches is right. This is not sort of a judgment on the existing stream processing frameworks. It's just that they chose to take a specific route, and we're trying to investigate something different. Both have their trade-offs. Frameworks, I'll point out, have a number of benefits as well, which are worth considering if you're deciding which of these systems to adopt. For one, they actually remove a lot of decisions that you would otherwise have to make. Figuring out how you actually want to deploy and monitor some of these things can be painful if you don't already have a system in place. A lot of times you may not be adding another system, so it's not sort of operational complexity that you're adding to. If you already have a Spark cluster and you want to run Spark streaming jobs, that's great. You can do that pretty easily. You'll already have all the necessary infrastructure in place. And they do provide a single centrally managed framework that, while it's a higher barrier to entry, might be more convenient for some organizations to manage. The library, on the other hand, fills a different gap. Easy to adopt, no assumptions about your existing infrastructure, fits into any existing strategy for operationalizing applications. So again, no judgment on either one. We actually love all of them, but we wanted to fill in a sort of a different design point in the space that we didn't think was being currently addressed. So now I want to dive into a few details of what Kafka Streams actually looks like. This is a small snippet of the Processor API, and actually pretty much all you need to know about the Processor API. It's super simple, and intentionally so. It's supposed to be the lowest level thing that you can do. The init and close methods are not super interesting. The key ones would be process and punctuate. And all process does is accept a key value pair. And so this is read directly out of Kafka. And from there, in the process implementation, you write the code for that, and you can do whatever you want in terms of keeping track of state, in terms of interacting with other systems, in terms of writing output back to Kafka. The second punctuate function is sort of the bare minimum thing that you need from the framework in order to support a bunch of the time-oriented features. So things around windowing in particular will need this. So very low-level API, but it ends up being powerful enough to build a bunch of stuff on top of it. One of the key features here is that these processors can be composed to form a graph of processors. These processors can live on the same machine, or they can be distributed. If they live in the same process, you may be able to sort of combine them without having to use any intermediate storage. So we may just pass messages between them in memory. If they cross process boundaries, then we're going to want to do something fault tolerant and scalable. And so in that case, we'll generally exchange messages via durable Kafka topics. There are a couple of reasons why these processor DAGs might span multiple processes. One could be just that you want to scale out processing, and sometimes it makes sense to actually implement different programs for different pieces of your pipeline, just to keep things simple and simple and decoupled. The other reason is that oftentimes if you're working in a larger organization, these DAGs are going to be composed of processors from multiple teams. So you may actually have applications written by separate teams, and Kafka is really the point that you want to use as the exchange of data. It provides that sort of fault-tolerant, scalable solution, and it's also sort of centrally managed, so generally teams don't need to worry about sort of interacting. There's an organizational decoupling that goes on there as well. So just to give you an idea of what it would look like to actually use one of these and write an application, this is it. Sort of absurdly short. It's obviously a little bit shorter than you need for a full program because I haven't included any of the processor implementations. But it really is just a matter of setting up enough information about how to connect to Kafka and then building this DAG. So you can see there's a builder add source, builder add processor, builder add sync. Obviously, more complicated DAGs would require a bit more effort, but then once you're done, it's all in a main method, and you call streaming.start, and it goes. Since it's just in a main method, it is just another program that you can deploy anywhere, however you want. And without even having to really think about it, you get parallelism and fault tolerance for free. I'm going to come back to the execution model in a minute. That processor API is probably going to be a little bit painful to use unless you really need it. It's pretty low level. You don't want to implement all of these things yourself. So we provide stream processing or a DSL on top of it. This actually doesn't look that much different. If you're familiar with things like Spark and Spark streaming, it's going to have a similar sort of feel to it. A little bit different since it's not Scala native, but the basic idea is that we can read in from a topic, and that generates a stream type object. From there, we can do all sorts of maps and aggregates, and we get back out more streams. Those streams are not necessarily, in that case, coming from Kafka. So if you just do a map and a filter, there's really no reason to store any data in Kafka. You can just do that inline. But then eventually you can write that data back out to Kafka. And again, this follows the same model where this would be the code that you would put in a main method, and you're done, and you can deploy however you want to. If you have Mesos and can just sort of like send the thing off and spin it up and down, or scale it up and down, then you're done. So how does this actually execute? Each of those processors, I guess I should say actually in this K-streams model, this is all built on top of the processor API. So it's all going to compile down to basically the same thing that as if you wrote the processors all manually yourself, except it's a bunch of pre-built tools. I guess the other thing worth mentioning here is that because this is a simple example that fits on a slide, we don't have a few other things that are included with Kafka streams here, including the concept around tables and joins are not shown here, but they are supported. Okay, so the execution model. Basically, each of these processors just maps to a set of tasks. In the simplest mode, we might be deploying just one of these tasks, and it will read from the input topics. It has some local state storage, which I'll come back to in a minute, and then it can write to some set of output topics. Or actually, it doesn't even have to write to those output topics. It could also just compute the state internally and run something like a service. However, we can also get sort of automatic scaling up and down. If we ask it to run 2 tasks in this case, what will happen is that the load balancing happens according to the input topic partitions. So we have multiple topics that we're reading from. Let's say in this case that we actually want to join data from topic A and topic B. In that case, they have the same number of partitions, and we balance the load between processor task 0 and processor task 1 so that the input partitions are balanced across them, which should approximately balance the total amount of data. And in particular, we can also be careful about how we do things like co-partitioning. It is important that partition 0 from both topic A and topic B make it to the same processor task. From there, this framework doesn't actually assume much about what these processors are doing, so it can then write data sort of arbitrarily to output topics. So you'll see that both of the processor tasks write to both output partitions for the output topic. So I want to come back to that state storage. So each processor has that little database that I showed, and it represents the processor's local state. Since state is local, reads and writes are going to be very fast. And state is also pluggable. You can choose to use an in-memory solution, or you can use a RocksDB instance. Those are the current implementations. Since it's pluggable, we could always swap out other storage systems. But if you use local in-memory state, that doesn't really sound very safe. Like, what are we going to do if something crashes and we need to bring up a process somewhere else? So if one of them does crash, what we do is handle that by using the same log structure to store a change log on that state. And so this ends up getting stored into Kafka as well. That change log is then highly available. And so even if you lose your processor state, your entire machine dies. Even if you had the RocksDB data, if your instance actually died such that your disk died, you would still be able to rebuild the change log from that changelog topic, or rebuild the data from that changelog topic. So Kafka Streams takes care to ensure that that state is fault tolerant, but it's mostly handled behind the scenes for you, and from your perspective, all of that access looks local, so it's just a quick reads and writes from in-memory or on disk. So I only talked logically about processor tasks, but they also are mapped to physical tasks. So you can map them to a single physical process, and we'll just have multiple threads running. Or you can map to multiple physical processes. And this is really where the value of this processor task abstraction comes in, because you can map it to different physical processes. That allows you to scale out across multiple machines, distribute across multiple machines. There's no need to have any additional coordination between them beyond the initial assignment of input topic partitions. And so from the perspective of the framework, the sort of key abstraction that we're providing is this task that runs forever and keeps this state permanently. It'll just keep on updating it forever. And if it fails, when it'll resurrect itself. That includes if one of the physical processes dies and you don't restore it, so much like consumer groups. Okay, so we also did a bunch of work around the concept of time. We actually didn't come up with a lot of this. This is something that came out of a paper from Google and a system called Dataflow that they built. They introduced these ideas. And their observation was that you can't actually depend on a window of stream data ever ending, since there will always be late arriving data. And so when dealing with time and stream processing, there are two concepts of time that are worth paying attention to. The first is event time, and this is what you might think of by default. It's basically whenever the event was created, you assign some timestamp to it, and you should be able to use that when doing any computation. This is sort of what, or the other is processing time, and that's when an event actually, hit that processor task, and you did something with it. So due to delays or bottlenecks, these two things might not be the same, but for a long time, stream processing frameworks were assuming that they are the same thing. It turns out these can diverge. If you have some sort of bottleneck or a network partition or some system goes down, you may actually not pick up that data until much, much later after it was created, and you may not process it until much, much later. This is actually probably the biggest source of incorrectness in many stream processing systems today, the fact that they don't account for this. They can't account for late arriving data, which means that if you do a window just based on your processing time, then if you have an event come in, even 5 seconds late, you're not going to account for it, and you're going to get incorrect values. Kafka Streams will account for this, and it can go back and update the old windows up to some limit. You're always going to have to put some limit on how far back you're willing to accept data from. So this plays out in kind of an interesting way with respect to windowing. As an example to understand this, imagine that you're building a sort of Google Analytics style dashboard, and you're counting visitors to your website by geographic region. And assuming that the window size you're interested in is 15 minutes. If I visit the website and from my phone, and before the event gets sent out, my phone either dies or I lose network connectivity or something like that, and it only comes back up some number of hours later. When that event makes it to the server, we don't actually want to update the current 15-minute window, but rather the one from 12 hours ago. So we need to be able to do that. What you're really windowing and counting by in this case is the event time and not the processing time. And so you need the stream processing library to be able to update previous windows. Windowing itself is actually a more complicated topic than you might think. There's a lot of details in getting it right and a lot of details in providing all of the library support for it. That's obviously something we're putting a lot of effort into with Kafka Streams, but it's something that if you choose to go the sort of do-it-yourself route, you're going to have to handle on your own. OK, so that sort of covers a bunch of the problems in stream processing and how Kafka helps address them. And then Kafka Streams builds on top of that to provide sort of the few additional missing pieces that you need. It turns out that Kafka Streams itself can actually be a relatively small implementation. But if we come back to this complicated Lambda architecture I showed earlier, it works. It can be a good way to go, but it's operationally definitely more difficult to run. We said we were trying to simplify this, so I want to sort of show an updated picture, which is what it ends up looking like with Kafka Streams, which is you have Kafka, you have your code, it talks directly with Kafka. You deploy it however you want. We don't have a lot of operations on top of that. It outputs to some other system like a database for whatever derived data you're trying to store, and then your app talks to that. So hopefully overall what this results in is fewer moving parts, and because it's sort of a modern implementation of stream processing and it takes into account all of these recent developments, it also gets a lot of the features like being able to actually correctly handle late arriving data. I want to also briefly mention Kafka Connect because I want to tie together sort of a bigger picture here in terms of how to use Kafka. So Kafka Connect is a new import-export framework. I'm not going to talk about it really in any depth, but the idea is to standardize the way that you get data into and out of Kafka. In a lot of ways, this is actually trying to do something a little bit opposite of what we're doing with Kafka Streams. So in particular, Kafka Connect is doing a lot of the hard work for connectors. There's a million Kafka connectors out there on GitHub that you can go and grab, and they vary wildly in terms of their, just generally in terms of quality, but in terms of the support for features, in terms of how they handle scaling out, whether they're fault tolerant, whether they have at least once or exactly once semantics. Kafka Connect is doing a bunch of the hard work here by handling a lot of these problems. And it's also doing this thing, which is why I said sort of the opposite of Kafka Streams, is that it's actually moving towards a sort of central management scheme, where it's a centralized cluster that you manage and maintain. In this case, that's actually a good thing because you don't want everyone that wants a connector, of which there are very, very many, to have to manage this on their own. And have to monitor a wide variety of different sorts of metrics. This doesn't actually, the same thing doesn't apply in Kafka Streams because you can standardize things a little bit more across applications there. So we provide sort of a centralized cluster that manages all of this for you. You just submit jobs and copy data. There's a bunch of open source connectors popping up. How this fits into the bigger picture is this concept of a stream data platform. And so what we have here is sort of at the top, Kafka Connect pulling in data from different data sources. And these are oftentimes your regular applications, your microservices that you would write and that might be generating data, or external users might be accessing them and generating data. So that top layer is actually your request response area. In the middle area, we have sort of the asynchronous stream processing layer, where we've got data into Kafka now, and now we can apply stream processing to it and get all sorts of interesting output data. So we can do real-time analytics, we can get aggregates, basically all of the transformations you might want to do for specific applications, things like online fraud detection, stuff like that. So that's sort of your intermediate layer where you want something real-time, but you need that additional processing. And then finally, both the original data and that derived data may eventually make it down into your sort of batch system. And something to take away from this entire talk is that while stream processing is a solution to many problems, and oftentimes we think of batch as being a special case of stream processing, those systems are still optimized in a certain way that is going to be hard to accomplish directly with Kafka. So definitely still have use cases. You definitely still want those batch systems there and want the data to eventually flow in there. Kafka Connect will also help you get that data in there. And so the founders of Confluent spent a long time building this type of platform at LinkedIn. They did it from scratch without sort of this framework in place yet. And it's now sort of taking hold across a bunch of companies via a bunch of open source software, including Kafka itself, Kafka Streams, and Kafka Connect, both of which are part of the core Kafka project, as well as a bunch of tooling that Confluent has built around it to help make this easier to manage. The result is now LinkedIn processes more than 1.2 trillion messages a day. I think that number is up to date. And that's sort of their entire feed of data. Basically, everything goes through what we refer to as sort of central nervous system for them. Kafka is a central nervous system of their data pipeline. And with that, I'd like to conclude. Twitter is up there. If you like this type of content, we are very verbose bloggers. We have a lot of content on there. And if you want to try any of this stuff out, please download Apache Kafka and Confluent Platform. The link's there. And that includes, by the way, a preview release of the Kafka Streams API. Thanks.